Okay, so today we are going to solve an LPP by solving its dual. Okay, from the dual table, from the optimal dual table, you will get the answers of the primal LPP. Okay, so we'll see how we have to do that. So before we start doing the problem, first of all, we have to see some steps that we have to do. We have to do it in the same order. Okay, only then we'll get the correct answer. So the main things we have to check over here is, first of all, convert the given LPP, the primal LPP into the dual. Okay, and then solve the problem by simplex or big M method. Okay, so before solving for the dual, what will you check? You will first of all check if there is any unrestricted variables. If there are any unrestricted variables, you will replace it by, for example, if x1 is the unrestricted variable, then you will replace it by x1 dash minus x1 double dash. Okay, we have seen that in the previous class. Then you have to convert it into the canonical form. Canonical form means if it is maximization problem, all the constraints should be of less than or equal to type. And if the LPP is of minimization type, then all the constraints should be of greater than or equal to type. Okay, so converting it into that type is called as canonical form. Okay, once that is done, you take the canonical LPP and then convert that into the dual. Okay, so all the variables that you check for converting into dual should be from the canonical form. It should not be from the question. Okay, the primal question that is given, it should not be from that. From where you took the canonical question, no, the canonical form, from that you have to take all the variables and coefficients for converting into dual. Okay, so once dual is done, what you do, your immediately next step is you have to solve for the simplex or the big M method. Okay, we have already told in our first classes, for solving by simplex or big M method, first of all, you have to check if it is a minimization problem. Okay, if it is minimization problem, we immediately convert that into a maximization problem by multiplying the objective function with -1. Okay, and at last you will get an answer. You have to multiply that again with a minus sign. Only then you will get the correct answer. Okay, second thing that you check in the simplex method or big M method is the right hand side of all the constraints should be positive. Okay, again, if that is not positive, you have to multiply both sides of the constraint with -1. Okay, and then you will finally decide whether we have to solve it by simplex or the big M method. Okay, for all the constraints are of less than or equal to type, we will go for simplex method. Okay, or if any of the constraints are of greater than or equal to type or equal to type, then we will go for big M method. Okay, so with that introduction, we'll start today's problem. What is the problem? It is written as write down the dual of the LPP and solve it. Okay, or that question can be asked as write the solution for the primal. Okay, in that case also you have to convert that into dual and then take the answer for the primal from that dual optimal table. Okay, the last one is the present question can also be asked in this form. Okay, prove using duality theory that the LPP is feasible but has no optimal solution. That is, the solution is unbounded. Okay, your existence theorem. What does the existence theorem say? If any of the primal or the dual, okay, if any of that is infeasible, then the corresponding dual or the primal, that will be unbounded. Okay, so this is what the existence theorem says. Okay, so infeasibility, how do you check for infeasibility? Okay, in our optimal simplex table, we have all Cj minus Zj as less than or equal to 0. But in the basic column, we have an artificial variable. Okay, in such situation, we'll say the LPP is infeasible. Okay, in such case, the dual will have unbounded solution. Okay, or in a case where you got the primal as unbounded. Okay, and what will be the dual? Dual will be infeasible. Okay, is it clear? So in our question, they are asking us, prove using duality theory that the LPP is feasible but has no optimal solution. Okay, so it is enough to prove that. What should we prove? In our dual, if we prove in the dual table, we are actually going to convert it into the dual form. No, in the dual form, if you are able to prove that it is infeasible. Okay, infeasible means the optimality condition has been reached, but the basic variable column has artificial variables. In such situation, we say it is infeasible. Okay, so in the dual table, you prove that it is infeasible. Then what can you prove? According to existence theorem, you can prove that the primal is unbounded. Okay, so that is what is asked in the question. So in the dual, you prove it as infeasible. So by existence theorem, you can prove that it is unbounded in the primal LPP. Okay, clear? So you will understand more when we solve the question. Okay, so in our current LPP, this is the LPP that is given for us. Over here, we have two constraints of greater than or equal to type. Okay, so they have asked us to solve this LPP by solving the dual. Okay. So how will we start? Here we don't have any unrestricted variables. Everything is given as x1 and x2 greater than 0. Okay. Unrestricted means x1 and x2 can take any of values, positive or negative. That is why it is told as unrestricted. No restrictions on the sign. Okay. In the question, sometimes they'll give x2 is unrestricted or x1 is unrestricted. What is the meaning? X1 can take any values, positive or negative values. Okay. But in our this question, what is it given? X1 is greater than 0 as well as x2 is also greater than 0. That means x1 and x2 will take only positive values. Okay, in that case, we don't have to replace it with any of the previously told things. We don't have to do. Immediately, we can convert this into the canonical form. Okay, canonical form, what is the meaning? This is the maximization problem. So all the constraints should be of less than or equal to type. Okay, so I'm writing it. Okay. First, convert the primal LPP into canonical form. Okay. How will you do that? Maximize z is equal to 4x1 plus 2x2. The objective function will remain the same, but here we have the constraints subject to, I will multiply on both sides with -1. So minus of x1 minus of x2. Here the symbol will reverse. So it is less than or equal to -3. Similarly, second constraint minus x1. Here minus and minus, it will become plus. Okay, x2. Again, symbol will reverse. Less than or equal to 2 will become -2. Okay, then you have x1 comma x2 greater than or equal to 0. So this is our canonical form. Okay, so if you get the canonical form, what will we do? We will take the body of the matrix. Okay, body of this primal matrix. So body of the primal matrix, I'm calling it as A, is equal to, here -1, -1, -1, -1, here -1 and 1. Okay, this is our matrix A. Okay, now we are going to take the transpose. Okay, transpose is written as A raised to the power of T. Okay, how will it become? -1 and -1, you will write this into the vertical form. So -1, -1. Again, -1 and 1, -1 and 1. Okay, so this is the body of the transpose matrix. This is going to be the body of the dual. Okay, so in here, how many constraints do we have? In the canonical form, this is our canonical form. How many constraints do we have? We have two constraints. Okay, yes, two constraints. So we'll have two variables in the dual. Okay. So since the primal LPP has two constraints, the dual will have two variables, namely W1 and W2. Okay, you can even name this as Y1 and Y2. That is no problem. Since in the question it is all of the form X, no, so you can even name it as Y1, Y2, no problem. But I am taking it as W1 and W2. Okay, so you have to take the canonical form over here. The canonical form is there here. Okay, take this and then you will convert it into the dual. Okay, therefore the dual is given by, okay, here it is maximization problem. So in our dual we'll have minimize z dash is equal to, okay, the objective functions coefficients will be the right hand side of our canonical primal LPP. So it is -3 and -2. No? So here I'll write -3 and -2. What are our variables? W1 and W2. Okay, so we have written the objective function for the dual. Next, we have to write the body of the matrix. Okay, for writing the body of the matrix, we already have the transpose matrix. Okay, so here I will write subject to. Okay, subject to. Here I have -1, -1, -1, again -1 and 1. -1 and 1. Here I will take W1. This one will be W2. Okay. Now this is our minimization LPP. So our symbol will be greater than or equal to. Okay. Next, the right hand side of the dual will be the coefficients in the objective function of the canonical form. Okay. So this is our canonical form. What are the coefficients of the objective function? It is 4 and 2. Okay. So the right hand side of the dual will be 4 and 2. Okay. Is this clear? Okay, then finally we have W1 comma W2, it is greater than or equal to 0 because that is our non-negativity constraint. Okay, so the dual we have done with the dual. Next part of the question is we have to convert this into the simplex form. Okay, for getting the solution, we need to get the value of W1 and W2. For that, we will solve the LPP. Okay, what are the methods for solving the LPP? We have simplex method, we have big M method, etc. Okay, so when we start the simplex method, what we have to check? We have to check if the objective function, okay, is of maximization type. Okay, over here it is not of maximization type, so we have to convert it into maximization type. Okay, so we know minimization of z dash is equal to minus of max of minus z dash. Okay, here it is z dash, no? So that is why I have taken here as z dash. Okay, dual we'll always represent as dash with a dash. Okay, so now I'm taking only this much. Okay, so max of minus of z dash, I'm taking it as max of z dash star. Okay, where max of z dash star is equal to max of minus z dash. Okay, just instead of this minus, no, I'm replacing it with z dash star. That is all the difference. So I have written it over here also, max of minus z dash. That is this one. I am taking it as max of z dash star. Okay, I have not made any changes. Just replace this minus with the star. Okay, so next one, max of this one, z dash star is equal to, we have to take this minus inside, no? So minus of, which is our objective function? This is our objective function. Okay, this is what we are going to convert it into max form, no? So minus of this one, minus 3w1 minus 2w2. Okay, so what will be our max function? Max of z dash star is equal to, I'm going to take this inside. So minus and minus, it will become 3w1 minus and minus again plus 2w2. Okay, so this is our objective function for the simplex problem. Okay, again you check over here in the simplex problem what we should do. We have to replace all the inequalities by the equal to sign, no? So for that what we should do, here it is greater than symbol and here it is also greater than symbol. So how will we replace it? Minus of surplus variable plus we will add the artificial variable. Okay, similarly here also it is greater than or equal to, so we'll minus S2, that is surplus variable, and add artificial variable A2. Okay, and we have to introduce S1, A1, S2, A2 into the objective function. Okay, so I'm taking these constraints down. Okay. Okay, for time being, I'm just writing the constraints as such. Subject to minus 1w1 minus 1w2 greater than or equal to 4. And minus 1w1 plus 1w2 greater than or equal to 2, w1 comma w2 greater than or equal to 0. Okay, now we have the objective function, we have the two constraints, we have to convert it into the form wherein we have surplus variables and artificial variables. Okay, so adding surplus and artificial variables. Okay, we have the constraints subject to, what will our constraints be? It is minus w1 minus w2 Okay, here we have the greater than symbol. Instead of that, I'm putting minus S1 plus A1 equal to 4. Okay, similarly, second constraint also we have greater than or equal to. So it is minus W1 plus W2 minus of surplus variable. I'm going to use S2. Okay, it will be minus here plus A1. We have already seen in the big M method, no? Since it is already greater than or equal to, we have to use the big M method. Equal to, here we have 2. Okay. Sorry, A2. Yeah. A2 is equal to 2. Okay. Now we have the non-negativity constraint W1, W2, S1, S2, A1, A2 all are greater than or equal to 0. Okay. Then we have to introduce all these new variables into the objective function. So we have the objective function is this one. Okay. We are going to add all those variables into the objective function. Max of z dash star is equal to 3w1 plus 2w2 plus when I'm introducing those variables into the objective function, all the slack and surplus variables will be added with the coefficient 0. Okay, so s1 plus 0 s2 and the artificial variable, they will get a coefficient of minus m. Okay, so minus m a1 minus m a2. Okay, so this is our final simplex table initial form. Okay, now we have to introduce all these things into the simplex table. Okay, so we have the initial simplex table. We are going to introduce all these variables into the simplex table. Okay, so here we have the coefficient of the objective function Cj. What are the coefficients? Here we have 3, 2, 0, 0, minus m and minus m. Okay, 3, 2, 0, 0, minus m and minus m. Okay, what are the variables? W1, W2, S1, S2, A1, A2. Okay, then introduce the constraints. Minus 1. Here we have minus 1 for S1. Okay, here we don't have S2, so it will be 0. A1 we have coefficient 1. A2 we don't have any coefficients. Okay, so it is minus 1, minus 1, minus 1. S2 we don't have in the first constraint. A1 we have 1. A2 we don't have. And the solution for the first constraint is 4. Okay, this is XB. This is our minimum ratio. XB is also called as the solution. Here we have the basic variable represented by B, and here we have the coefficient of basic variable. Okay. Now next constraint, second constraint, here we have minus 1, 1. We don't have S2, so its coefficient is 0. Sorry, we don't have S1, the coefficient will be 0. We have S2, the coefficient is minus 1. Then again, we don't have A1, the coefficient will be 0. We have A2, the coefficient will be 1. Okay, so introduce them. Minus 1, 1. S2, S1 we don't have 0. S2 we have minus 1. A1 we don't have, it will be 0. A2 we have 1. Finally, the answer is 2. Okay, now go for your identity matrix so that we have to introduce variables into the basic column. Identity matrix is given by 1, 0, 0, 1. Here 1 corresponds to the first row and the variable is A1, coefficient is minus m. So in this first row, I'll be writing over here A1, coefficient is minus m. Similarly, in the second row, we have 1 over here. So in the second row, the variable is going to be A2 and minus m. We have A2 and minus m. Okay, after doing so much, we'll go for Zj and Cj minus Zj. Okay, you already know all this now, so I'll do a little fast. Okay, Zj is going to be 2m, 0, m, m, minus m, and minus m. Okay, so in effect, what will happen? This is a positive value, this is a negative value. But since this m is very big, the coefficient of this m is minus 2. So in effect, this value is going to be a very, very big negative value. Okay, so we cannot have 3 minus 2m as a positive value because minus 2m is a very, very big negative value as compared to 3. So what will happen? In effect, this entire number is going to be a negative number. Okay, Cj minus Hj values, we will check only for the positive values. Okay, so this is a negative value. This one is negative, this is negative, this is 0, this is 0. So we are only need to check this positive 2. Okay, here it is positive 2. So Cj minus Hj will only take positive values for deciding the entering variable. Okay, here it is 2. So we'll take this one as the entering variable. So W2 is going to be the entering variable. Okay, is it clear now? So Sana, clear? Okay. So now we have to decide for the minimum ratio. Okay, minimum ratio we have to decide by dividing the XB column with the key column. Key column is W2 over here. So 4 divided by -1. We don't have to enter it because it is a negative value in the key column. Okay, so we'll just put a dash there. Second number is 2 divided by 1, which is 2. So this is going to be the outgoing vector. Okay, we have the key element as 1. Okay, this A2 is going to be the outgoing vector. Okay, begin method, we have already told that if the artificial variable is going out, then in the next simplex table, we don't have to consider the corresponding column. So A2 is going out, so we'll cancel A2 from the next simplex table. So I'm just cancelling here. Okay, so now we'll see the entering variable is, or entering vector is W2, and the leaving vector is A2. Okay, perform the row operations. Okay, R2 new, we have to start with the key row. Okay, R2 new is equal to R2 old divided by what is the key value, that is 1. So it is going to remain the same, which is R2 old. Okay, next one we have to change the first row. R1 new is equal to R1 old minus of what is the element corresponding to the key element in the first row, that is -1 into R2 new. Okay, so how will you do it? R1 old, we have -1, -1, -1, 0, 1. We don't have to take the 0 over here, skip it and take 4. Okay, so we have -1, -1, -1, 0, 1 and 4. Okay, minus of -1 into we have to take R2 new. R2 new and R2 old are going to be the same. So you can just take the values from the simplex table itself. Okay. -1, 1, 0, -1, 0. You don't have to take this 1. Skip and take 2. Okay. 2. Now over here, -1 and here minus into minus into minus. 3 minus is, it is always a minus. So it is -1. Together you have -2. Okay. Next one, -1 into, it is minus into minus. So it is plus. So -1 plus 1, which is 0. Next one, -1, because you already have a 0 here. Now over here, minus into minus into minus, it is a -1. Then 1 minus, see here, minus into minus, you have plus. Okay, sorry, here you have 1 into 0 also, no? So it is 1. Okay, next one, 4 minus into minus means plus. 4 plus 2 is 6. Okay, with these values, we can draw the first iteration of the simplex table. Okay, Cj is going to remain the same. We can just take it down from here. Okay, here you don't have to take the value for A2 and -m. Skip that full row and write the others. So here we have 3, 2, 0, 0 and -m. Okay, corresponding variables are W1, W2, S1, S2 and A1. Here I have the solution column XB. Here I have minimum ratio. Then over here I have a basic variable. Here I have the coefficient of the basic variable. Okay. We have already calculated R2 and R2 old are going to be the same. So just copy this row from the old simplex table itself. So the values are -1, 1, 0, -1, 0. Don't take this 1, skip it. Okay, and write 2 there. Okay, next one, R1 new is all these values here. So take it down. -2, 0, -1, -1. Here I have 1 and 6. Okay. Now, in our previous table, A2 is the leaving variable, W2 is the entering variable. W2 has a coefficient of 2. Okay. So I'll write over here W2 coefficient 2. Okay. A1 and -m will remain the same. A1 and minus M. Okay. Finally, we will go for Zj. Okay, what is the value of Zj? Minus 1 into minus 2 plus 2 into minus 1. Okay, the value will be, sorry, here it is minus M, no? So here also we have minus M. Okay, so minus M into minus 2, that is 2M. 2M plus 2 into minus 1. So that is minus 2 plus 2M. Okay, next value. Okay, next value minus M into 0 plus 2 into 1. What is the value? It is 2. Okay, here minus 1 into minus M into minus 1, that is M, plus 2 into 0. So we have just M. Then minus M into minus 1, that is M, plus minus 2. So it is minus 2 plus M. Okay, here I have minus M into 1, that is minus M, plus 2 into 0, that is 0. So here it is minus M. Okay, then we have Cj minus Zj, 3 minus of minus 2 plus 2M. So 3 plus 2. Okay, that is 5. Then again minus 2M. Okay, how will we calculate this value? It is 3 minus of, see, Cj minus, no, that minus here. Then again minus 2 plus 2M. Minus 2 plus 2M is this value. So 3 minus of minus is plus 5. Then minus into this plus. So it is minus 2M. Okay, so that is why it is 3. So 3 plus 2 here. 3 plus 2 is 5 minus 2M. So it is 5 minus 2M. Okay. Next one, 2 minus 2, 0. 0 minus M, minus M. 0 minus of minus 2 plus M. That is 2 minus M. Next one, minus M, minus of minus M. That is 0. So see over here, this value, it is a negative number because we need to consider only the M value. Okay, any number that has the M value with it. Okay, you need to consider the coefficient only of the M value. Here M value has a coefficient of minus 2. So entirely this value is going to be a negative number. Okay, this is 0. This is minus M, negative number. Over here also it is 2 minus M. So it is minus 1 over here. It is entirely, this is going to be a negative number. So it is 2 minus M is a negative number. Again 0. Okay, so we have reached the optimality condition. Okay, in this optimality condition, go and check the basic variable column. Here we have an artificial variable. So what is the meaning of that? This dual LPP is a infeasible solution, has infeasible solution. Okay, so I'll write it there. Therefore, all Cj minus Zj is less than or equal to 0 and an artificial variable A1 is present in the basic column. Thus, the dual problem does not have an optimal feasible solution. Okay, then according to existence theorem, therefore according to existence theorem, okay, there exist no finite optimum solution to the primal problem. Okay, primal LPP, that is solution is unbounded. Okay, so what is according to our existence theorem? Existence theorem says that if any of the primal or dual, over here dual problem, we are having a, we don't have a feasible solution. That means it is infeasible. Okay, in our dual it is infeasible. So what happens to the primal? What happens to the primal? According to the existence theorem, it will be unbounded solution in the primal problem. Okay, that is what our existence theorem says. Okay, so in our question, they have asked the same thing. Prove using duality theorem that the LPP is feasible but has no optimal solution. Okay, if you are having an unbounded solution means the solution occurs at infinity. Okay, there is a solution. That is why we are telling it is feasible. Okay, unbounded means there is a solution, it is feasible, but there is no definite optimal solution. Okay, the solution occurs at infinity. That is, it is an unbounded solution. Okay, hope you understood the problem. So that is why we have all Cj minus Hj value, it is negative or less than or 0. Okay, in that condition, we have an artificial variable occurring in the basic. Okay, that means this dual problem has infeasible solution. So according to existence theorem, if the dual has infeasible solution, then the primal will have unbounded solution. Okay, so the question we have proved it. Okay, so hence proved. Okay. Hence we have proved it. Okay.